The darkness of the European night was absolute. In the freezing heights above occupied Germany, a solitary bomber cut through the sky at over 20,000 feet. It was March 1943, and inside that aircraft, something was happening that would change the course of the war and the history of technology forever. A young engineer, surrounded by wires, valves, and improvised equipment, was about to achieve the impossible. His name was little known outside secret military circles, but what he was doing at that moment would transform aerial warfare once and for all. This is the story of how a solitary genius, armed only with knowledge, determination, and limited resources, built the first functional airborne radar system inside a bomber in full flight over enemy territory. A story of innovation born from desperation, of genius forged under extreme pressure, and of how science can change the destiny of entire nations. If you're enjoying this story, subscribe to the channel and leave in the comments the time you're watching this video. Your participation helps us continue bringing incredible stories like this one. To fully understand this extraordinary story, we need to go back in time. We need to understand the context of a war that was transforming Europe, of a technology that was barely leaving the laboratories, and of a man whose brilliant mind saw possibilities where others saw only impossibilities. The year was 1939, and the world was rapidly plunging into a conflict of unprecedented proportions. Germany had invaded Poland, and European nations were preparing for what was to come. But while armies marched and diplomats negotiated, a silent battle was already underway, a battle for technological supremacy. Radar was not a completely new invention in 1939. Scientists in various countries had been experimenting with radio waves and their ability to detect distant objects since the 1930s. The principle was elegant in its simplicity. Emit radio waves in a specific direction. If these waves encounter a solid object, they will return. Measure the time it takes for the echo to return, and you can calculate the distance to the object. It seems simple on paper, but reality was infinitely more complex. The first radar systems were monuments of engineering, occupying entire buildings, consuming enough energy to light a small town, and even then offering only rudimentary information about the position of enemy aircraft. Britain had invested heavily in radar during the years leading up to the war. The British Home Chain Detection System, known as Chain Home, was a network of radar stations along the British coast. These enormous towers, with their antennas rising dozens of meters high, could detect enemy aircraft approaching across the English Channel. During the Battle of Britain in 1940, this system proved its invaluable worth. For the first time in history, defenders could see the enemy coming with enough advance notice to organize an effective response. But there was a fundamental limitation. These radars were fixed, anchored to the ground, defending only the areas they could reach with their radio beams. Meanwhile, aerial warfare was evolving rapidly. British bombers flew to Germany night after night, trying to hit factories, refineries, and transportation centers that fueled the war effort. But bombing at night was an almost impossible task. Navigation was done by estimation using compasses, maps, and when luck allowed, glimpses of geographical features illuminated by moonlight. Crews flew for hours over hostile territory, never knowing exactly where they were, dropping their bombs based on guesswork and hope. The error rates were staggering. Subsequent studies would show that, in the early war, less than a third of bombs fell within 5 miles of the intended target. It was a catastrophic waste rate, both in terms of resources consumed and risks faced by the crews. It was in this desperate context that the urgent need arose to place electronic eyes on the bombers themselves. If an aircraft could see through darkness and clouds, if it could map the terrain below even on the blackest night, then aerial warfare could be transformed. But how? Ground-based radars were the size of buildings. How could anyone miniaturize this technology enough to fit in an airplane? How could it be powered with the limited energy available on board? How could it be made to work in an environment of constant vibration, extreme temperatures, and electromagnetic interference from all the aircraft's own systems? These were the questions that tormented Britain's best scientists and engineers. In secret laboratories scattered across the country, teams worked day and night, trying to solve these seemingly insoluble problems. One of these places was the Telecommunications Research Establishment, located in Malvern, a quiet town in the English countryside that had become one of the most important centers of British war technology research. It was there that our protagonist worked, a young engineer whose name, for reasons of security at the time and respect for his family's privacy, we will simply call Alan. Alan was not a genius in the cinematic sense of the word. He didn't have disheveled hair, nor did he speak in incomprehensible equations. He was a quiet, methodical man with an extraordinary ability to visualize complex systems in his mind. Coming from a modest family in northern England, he had won a scholarship to Cambridge, where he specialized in physics and electrical engineering. When the war began, he was finishing his doctorate on the propagation of radio waves under different atmospheric conditions. It seemed like an obscure academic topic, but it proved to be exactly the knowledge his country desperately needed. Alan was recruited to Malvern in early 1941. His initial work involved incremental improvements to existing radar systems, circuit adjustments, antenna optimization, receiver calibration. It was important work, but frustrating for someone of his capability. He saw the bigger problem. He understood that while radar remained confined to the ground, its potential would remain fundamentally limited. He began working on his own parallel projects, using his free time and discarded resources to experiment with radically different designs. Alan's approach was different from most of his colleagues. While others tried to miniaturize existing systems while maintaining their basic architecture, Alan rethought everything from the ground up. He realized that an airborne radar didn't need to have the same range as a ground system. It didn't need to detect targets hundreds of miles away. It only needed to see enough to navigate, to identify terrain features, to find targets on the ground. This meant it could use less power, smaller valves, more compact antennas. But it also meant it needed to be much more precise, much more sensitive, because it would be processing echoes from objects on the ground, not aircraft in the air. For months, Alan worked on his prototype. He soldered circuits late at night, tested components on weekends, made calculations in notebooks that filled entire drawers of his desk. His colleagues found him eccentric, even obsessive, but his superiors began to notice. There was something in Alan's work that showed real promise. When he finally presented his preliminary design in a tense briefing in the fall of 1942, the reaction was mixed. Some called him a visionary. Others called him crazy. The design was too radical, depended on technologies that hadn't been fully proven, required manufacturing precision beyond what British factories were accustomed to producing. But the war was not going well for Britain. The bombers continued to face major challenges, and their effectiveness remained questionable. Military leadership was willing to try anything that could offer an advantage. Alan received approval to build a functional prototype, but with a rigorous condition. He would have 6 months. If he couldn't demonstrate real results by then, the project would be cancelled and resources redirected to other initiatives. 6 months to do what many considered impossible. Alan assembled a small team. No more than 6 people, each chosen for specific skills. There was a radio valve specialist, a precision mechanic, 2 experienced technicians, and a young mathematician whose ability to perform complex calculations mentally impressed even Alan. They worked in an isolated hangar, separated from the rest of the establishment, under absolute secrecy. Even other researchers at Malvern didn't know exactly what was happening behind those locked doors. The first months were brutal. Each component presented its own challenges. Valves overheated or broke with simulated vibrations. Circuits interfered with each other, creating noise that masked the signals they were trying to detect. The antenna, which needed to be compact but efficient, went through dozens of iterations. Alan slept in the hangar many nights, waking suddenly with a new idea, running to his workbench to make adjustments before the insight was lost. But slowly, painfully, the system began to take shape. Alan had opted to use a higher frequency than conventional radars, something that allowed smaller antennas but required more precise components. He developed an ingenious signal processing system that filtered out noise from the engine and other electrical systems of the aircraft. He created a visual display that presented information in a way that an operator could interpret quickly, even in the stress and confusion of a combat mission. In February 1943, with only a few weeks before the final deadline, the prototype was ready for initial tests. They installed it in a Wellington bomber that had been retired from combat operations and converted for experimental use. The first test flight was on a cold, clear morning. Alan was not a pilot, but insisted on being aboard as the system operator. As the Wellington climbed over the English countryside, Alan was kneeling in front of his equipment, watching the greenish circular display, adjusting controls, making frantic notes. For long minutes, nothing, just static snow on the screen. Alan felt his stomach sink. Had he made some fundamental error? Had he wasted months of work? Then, gradually, patterns began to emerge from the static. Vague shapes at first, but becoming clearer with each second. Alan could see the outline of the coast below, saw cities as brighter spots against the darkness of the countryside, even saw large buildings individually. It worked. It really worked. For the first time in history, an aircraft could see through clouds and darkness, mapping the world below with electronic eyes. Subsequent test flights confirmed and expanded this initial success. The system not only worked but exceeded expectations. It could distinguish terrain features with surprising clarity. It could detect specific targets, such as bridges and factories, at distances of several miles. And crucially, it was reliable. Flight after flight, it continued operating, withstanding vibrations, temperature changes, the brutal demands of the aeronautical environment. But demonstrating that something works under test conditions is one thing. Making it work in real combat is something completely different. Military leadership wanted a definitive demonstration. They wanted the system tested under real operational conditions, over enemy territory, under threat from fighters and anti-aircraft artillery. It was a risky and complex requirement. If the aircraft were shot down, not only would the system be lost, but the Germans could recover it, study it, develop countermeasures. Alan argued strongly against putting the prototype at risk in this way. He proposed more testing, more refinements, the construction of production units that could be risked in combat while his prototype remained safe. But the pressure was intense. The bomber offensive was intensifying, and operational difficulties were increasing. Each night that passed without this system represented wasted resources and reduced the effectiveness of the bombing campaign. Finally, a compromise was reached. There would be an operational mission, but over a low-priority target, on a night of good weather conditions, with a route planned to minimize exposure to enemy defenses. The mission was scheduled for the night of March 17, 1943. The target was an industrial complex near Bremen, Germany. It wasn't a target of high strategic importance, but it was sufficiently within enemy territory to constitute a real test. Alan would spend the entire mission operating his system, guiding the bomber to the target and, crucially, verifying whether it could really make the difference between random bombing and precision bombing. The days leading up to the mission were tense. Alan reviewed every circuit, tested every valve, calibrated every component multiple times. The crew of the bomber that would fly the mission was carefully selected. They were veterans, men who had survived dozens of missions over Germany, who understood the risks and knew how to react when things went wrong. They received a special briefing about Alan's system, about how it would work, what to expect, how to use its information. The pilot was a squadron commander named James, a calm and competent Scotsman who had flown Wellingtons since the beginning of the war. He was skeptical about the whole mission. He had seen many technological marvels that failed under the brutal conditions of real combat. But he respected Alan, respected the ingenuity he saw in the system, and was willing to give it a chance. On the afternoon of March 17th, Alan and the crew prepared. The Wellington was carefully inspected, fuel added, bombs loaded. Alan's radar system was installed in the central section of the fuselage, its cables running to the cockpit where a display had been installed in a position where both the navigator and bombardier could see it. Alan would have his own station, surrounded by his equipment, able to make adjustments and monitor the system's performance throughout the flight. When the sun began to set, casting long shadows over the airfield, the crew boarded. Alan carried a bag full of tools, spare parts, and notebooks. If something went wrong, he would need to be able to make repairs in flight. The thought was simultaneously exciting and terrifying. The Wellington's engines roared to life, the propellers spinning until they became blurred discs. James executed his pre-flight checks meticulously, then signaled he was ready. The control tower gave clearance, and the bomber began to roll down the runway. The takeoff was smooth. The Wellington climbed into the twilight, turning east toward the English Channel. As they climbed through layers of clouds, the world below disappeared. This would be the first major test of the system. Could it navigate through thick clouds? Alan turned on his equipment, watching anxiously as it warmed up. The valves began to glow with their characteristic amber tone. The circuits hummed softly, and then, magically, the screen came to life. Through the clouds, through the growing darkness, Alan could see the coast of England receding behind them, the channel stretching ahead like an empty area, and beyond, faintly, the coast of occupied Europe. The channel crossing was tense. This was territory where German night fighters patrolled, where anti-aircraft batteries were always alert. But the Wellington passed unchallenged, slipping into German airspace like a ghost. Alan was totally focused on his screen, making small adjustments to the controls, noting readings, guiding the navigator with constant updates of their position. The system was working perfectly. He could see cities below, distinguish rivers and railway lines, identify landmarks that confirmed they were exactly where they should be. The route to Bremen took them over rural areas, avoiding the major concentrations of air defenses. But even so, occasionally they could see traces of anti-aircraft fire rising from the ground, blindly searching for invaders in the night. Once, a searchlight briefly illuminated them, and James dove the bomber in an evasive maneuver that left Alan struggling to stay with his equipment. But the searchlight lost them, and they continued east. As they approached Bremen, Alan began searching for the specific target. The industrial complex should appear as a characteristic pattern on his screen, a cluster of large buildings surrounded by open areas. Initially, the city was too confusing, too many echoes overlapping. But Alan adjusted the sensitivity, focused the beam, and there it was. Exactly where intelligence had said it would be, a complex of large buildings that could only be the target factories. He passed the coordinates to the bombardier. The bombing approach began. Traditionally, this would be done visually or more often in the early war, by estimation based on time and speed from the last known landmark. But now, Alan could guide the bomber directly, making real-time corrections based on what he saw on his screen. Left a bit. Steady. Right. Steady. The bomber made its adjustments, aligning perfectly. When the bomb bay doors opened, Alan kept his eyes fixed on the screen, confirming they were exactly over the target. The bombs fell. Through the radar screen, Alan couldn't see the impacts, but the navigator, looking through an observation window, confirmed that the target had been reached. The industrial complex had been hit with precision. For the first time, a night bomber had attacked a target with something close to daylight precision, all thanks to Alan's system. The bombing mission was complete, but now came the most dangerous part. The escape. Bremen was on full alert now, knowing there were attackers in their area. Searchlights swept the sky. Anti-aircraft artillery created a defensive barrier over the city. James pushed the throttles forward, making the Wellington gain speed as it turned west. Alan continued operating his system, providing navigation guidance, helping them avoid the largest concentrations of defenses. They passed over an anti-aircraft battery that opened fire furiously, shells exploding dangerously close, the aircraft shaking with the shock waves. Shrapnel fragments hit the fuselage with sharp metallic sounds. Alan instinctively shielded his equipment with his body, praying that no critical fragment would be damaged. But the Wellington was robust. Despite some superficial damage, all essential systems continued functioning. And crucially, Alan's radar system continued operating perfectly. They emerged from the most intense danger zone and established a direct course home. The return trip was calmer. Alan relaxed slightly, allowing himself a brief moment of satisfaction. They had done it, really done it, proven that the system worked in real combat under the most demanding conditions imaginable. When they finally crossed back over the English coast, it was past midnight. Alan was exhausted but euphoric. He had spent 4 hours operating the system continuously, and it had functioned flawlessly. The landing was smooth, and when the Wellington's wheels touched the runway, Alan felt a wave of relief and triumph unlike anything he had ever experienced. They had changed aerial warfare. In that single night, over Germany, the future of precision bombing had been born. The days and weeks that followed were a whirlwind. The mission report quickly moved up the chain of command. The demonstration was considered a resounding success. Alan received orders to prepare his system for mass production. Engineers from factories across the country came to Malvern to learn about the design, to discover how they could manufacture it at scale. The system, now officially designated with a secret code name, began to be installed in operational bombers. But Alan didn't rest on his laurels. He knew this was just the beginning. The system had limitations, areas where it could be improved. He immediately began working on a second generation, incorporating lessons learned from the operational mission. More reliable components, more sophisticated signal processing, clearer and easier to interpret displays. His team grew from 6 people to dozens, then hundreds as the program expanded. Throughout 1943 and 1944, systems based on Alan's design spread through the bomber force. They revolutionized night operations. Industrial and military targets that were previously impossible to locate in darkness could now be identified with reasonable precision. The effectiveness of strategic bombing increased dramatically. More importantly, the safe return rate of crews improved. With better navigation and the ability to avoid the heaviest defenses, more airmen completed their missions safely. The Germans eventually discovered the new system. They found equipment in downed bombers, studied it, developed countermeasures. But the advantage had already shifted. Britain and later the United States, which adopted similar designs, maintained the lead in airborne radar technology for the rest of the war. And this advantage contributed significantly to the Allied victory. But what happened to Alan? His story, like so many stories of war scientists and engineers, disappeared into the mists of security classification. After the war, he briefly returned to academic life, but found it unsatisfying after the intensity and purpose of war research. He joined an electronics company, where he continued working on radar systems now for civilian applications. He helped develop the first air traffic control radars, systems that would make commercial aviation safe enough to become the global industry it is today. Alan never sought fame or recognition. He rarely spoke about his war work, even with family. For him, it was simply what needed to be done. His contribution at a time when his country and the world needed every ounce of talent and dedication. He lived quietly until the 1990s, passing away shortly before turning 80. Few of his obituaries mentioned his crucial role in the Allied victory, and those that did gave only the vaguest details, still restricted by security classification even decades later. But Alan's legacy lives on. Every commercial aircraft today flies with direct descendants of the technology he pioneered in that isolated hangar in Malvern. Every satellite navigation system, every weather radar, every sensor that allows machines to see the world through means invisible to the human eye, all trace their lineage back to those first bold experiments. The technology he developed in wartime also became a force for preserving lives, guiding aircraft safely through storms, helping predict weather, enabling global communications. Alan's story reminds us of something fundamental about innovation and human progress. They rarely come from moments of sudden inspiration or from solitary geniuses having epiphanies. Instead, they come from hard and persistent work, from thousands of hours spent solving incremental problems, from courage to continue when failure seems certain. Alan didn't invent radar. He didn't have some mystical vision of how to make everything work. He simply refused to accept that the problem was insoluble, worked methodically through each challenge, and had the luck and skill to be in the right place at the right time with the right skills. His story also reminds us of the human cost of war and the innovation born from it. While Alan worked in his hangar, young crews faced extreme dangers in bombers over Europe every night. While he tested circuits and adjusted antennas, cities were being affected by conflict, civilians faced the consequences of war, civilization was being tested to its limits. The technology he created helped protect Allied airmen, but also made the bombing of German military and industrial targets more precise, targets that, no matter how strategic, were located in areas where ordinary people tried to survive the war. This is the duality of technological innovation in wartime. It is driven by the best impulses, the desire to protect the homeland, help compatriots, combat destructive ideologies. But it also brings complex dilemmas, making conflict more technological, outcomes more defined, consequences more serious. Alan lived with this duality, and it marked him. Those who knew him after the war spoke of a certain seriousness in his eyes, a weight he carried. He was proud of what he had achieved, but also aware of all the implications of his work. In the post-war years, as radar technology expanded into civilian applications, Alan found some measure of peace. He could see his invention being used for constructive and peaceful purposes. He mentored young engineers, passing along not just technical knowledge, but also an ethic of responsibility. Technology, he insisted, is not neutral. It's not just a tool that can be used for good or evil with equal ease. The way it's designed, the purposes for which it's created, the consequences its creators anticipate or choose to ignore, all of this matters. Engineers and scientists, he argued, have moral responsibility for what they create. This was a radical argument in the 1950s and 1960s, when technocracy was on the rise and the prevailing belief was that technological progress was inherently good, that scientists should just create and let others decide how to use their creations. But Alan had seen too much, knew too much. He had personally experienced how war pressure could distort priorities, how urgent necessity could justify almost anything. And he was determined that the next generation think more deeply about these questions. Looking back now, more than 80 years after that crucial night over Bremen, we can see Alan's story in a broader context. He was one among thousands of scientists and engineers who were mobilized during World War II, each applying their particular talent to the urgent problems of conflict. Collectively, they transformed the war and, in doing so, transformed the world. The Manhattan Project created nuclear weapons. The cryptographers at Bletchley Park broke German codes. Chemical engineers developed new explosives and fuels. Doctors pioneered antibiotics and surgical techniques. And Alan and his colleagues revolutionized how machines could sense and navigate the world. All these advances had dual use. All could be and were used in different ways. Nuclear fission could power cities or be used in weapons. Cryptography could protect legitimate communications or hide questionable activities. Antibiotics could save lives from infections, but also enable riskier medical procedures. And radar could guide bombers to targets or commercial aircraft to safe landings. The difference lay in the choice, in the intention, in the wisdom of those who controlled the technology. This lesson remains deeply relevant today. We live in an era of accelerated technological innovation. Artificial intelligence, biotechnology, nanotechnology, quantum computing, all promise to transform our lives in ways we can barely imagine. And all bring profound risks as well as immense potential benefits. As a society, as a species, we face choices about how to develop and deploy these technologies that are as consequential as anything Alan's generation faced. We can look to Alan's story as a guide. Not because it gives us answers, because each era has its own unique challenges, but because it shows us the process. How to approach impossible problems, how to persist through failure, how to balance the urgency of immediate needs with considerations of long-term consequences, how to accept responsibility for what we create. Alan didn't have all the answers, but he asked the right questions. And in the end, that may be the most important skill of all. There's an epilogue to this story worth mentioning. In the 1980s, when much of World War II history was being declassified, a historian tracked down Alan and asked permission to write about his work. Alan reluctantly agreed, with one condition. He didn't want to be portrayed as a solitary hero. He insisted the story should include all the people who had contributed. The team that built the prototype. The pilots who risked their lives testing it. The factory workers who manufactured thousands of units. The operators who used it in combat. Progress, he insisted, is always a collective effort, never the work of an isolated genius. The book that resulted was modest in its circulation, read mainly by military history enthusiasts and engineers interested in radar development. But it captured something important: the humanity of technological innovation, the fact that behind every advance are real people, with hopes and fears, making difficult choices in impossible circumstances. It's not a story of technological inevitability or predetermined progress. It's a story of human agency, of decisions made by individuals who could have chosen differently. And in the end, perhaps that's what makes Alan's story so powerful. It wasn't the technology that changed the course of the war. It was Alan's choice to apply his talent to this specific problem. It was the choice of his superiors to support him. It was the choice of bomber crews to trust his invention. It was the choice of thousands of factory workers to manufacture it with care and precision. Each of these choices could have been different, and the outcome could have been drastically altered. Today, when we look at the sky and see aircraft crossing continents with routine safety, when we check weather forecasts that depend on weather radar, when we use navigation systems that trace back to these first experiments with radio waves, we are seeing Alan's legacy. Not just his technical work, but his choices. His choice to work for something greater than himself. His choice to persist through difficulties. His choice to accept responsibility for the consequences of his creation. His choice to pass along not just knowledge, but also wisdom. The story of how a genius built a radar inside a World War II bomber is not really about technology. It's about people. It's about what humans can achieve when facing seemingly impossible challenges. It's about the choices we make and how those choices reverberate through the decades. It's about responsibility and consequence, about innovation and its impacts, about hope and determination. It is, ultimately, a deeply human story about our endless capacity for innovation and our equally great need for wisdom to guide that innovation. As we close this story, it's worth reflecting on the words Alan would have shared near the end of his life. When asked what he would like people to understand about his work, he responded simply, "We did what was necessary at the time, but each generation must decide for itself what is necessary, what is right. There are no easy answers, only difficult choices and the hope that we have enough wisdom to make them well. That wisdom, that humility, that understanding that technology without ethics is dangerous, that capability without responsibility leads to disaster, may be Alan's greatest legacy. More than any circuit he designed or system he built, more valuable than any patent or publication, was this lesson he tried to pass along. And in our current world, where technology advances at an ever-accelerating pace, where the consequences of our innovations become more profound and irreversible, this lesson has never been more important. May the Lord God grant us the wisdom to use our gifts responsibly, the courage to persist through challenges, and the humility to recognize that every advance brings both dangers and promises. May we learn from those who came before us, honor their struggles and achievements, and make choices that leave the world better for those who will come after. Amen.